Do you hear me? Yes, everyone hears me? Okay. I want first to thank Nikki for inviting me to come here. It's been a great opportunity for me to see all of you. Nikki has asked me specifically to talk about physical processes, and I think following up on the two previous talks which have described how the ocean was absorbing CO2, here I come to looking at some of the processes. And also yesterday we discussed a lot on how the biological pump was important into driving carbon from the surface of the ocean to the interior. And today I want to focus mostly on the physical processes. And I'm going to start with really explaining what I'm going to talk about in the frame of the natural carbon cycle and in the frame of anthropogenic carbon, which are slightly different. So I'll start with very, very basic ideas to remind you what are the things I'm going to talk about. So this is a very simplistic representation of the carbon fluxes into the ocean. So that's the surface of the ocean here. You have an exchange of CO2 between the ocean and the atmosphere. And I have drawn another line here, which is the line between the surface ocean and the twilight zone. And basically what you have is the surface of the ocean, a conversion between inorganic carbon to organic material, and this organic material is sinking, and that's what we've discussed a lot yesterday. So you have one part of the export of the biological pump, which is due to the sedimentation of the cells, and another part which is physically driven and which is due to subduction, and we've mentioned a lot yesterday the subduction by submesoscale features. There's another part of the physical fluxes which are important, and which are the fluxes that drive abduction of DIC to the surface ocean, and some fluxes which drive the subduction of DIC from the surface to the deep ocean. And so today what I'm going to mostly focus on is on these physical fluxes of DIC in and out of the surface ocean, and I will also discuss this physical part of the biological pump. So if we think of the pre-industrial ocean, some very, very simplistic view is that the ocean, when you average over a long time scale, you average the internal variability, you average out the decadal variability, you have an equilibrium, and the biological pump is equal to the net flux of DIC that comes to the surface. You can assume that if you forget about the inputs from rivers, you have the net flux between the ocean and the atmosphere is 0. And so you have a balance between these fluxes and these fluxes. But the question is, how big are these gross fluxes, the input and the output, compared to these two fluxes? This is something we know much less about. How are the gross fluxes of DIC? Are they much larger than the biological pump, or are they not? Something else we don't really know is how large is the subduction of organic carbon, this red curve, compared to the sedimentation of organic carbon out of the ocean. We have some estimates, but still there's a big unknown regarding the comparison of these two arrows. And also something else that we don't know is what are the regional distributions of these carbon fluxes. So we still don't know exactly the magnitude and distribution on a regional scale of all of these fluxes. If we think of the more contemporary ocean, my point is we've looked at, the two previous talks I've discussed this in great detail. The point where I want to go here is that we know the ocean has absorbed carbon, and there are good chances that this absorption is mainly achieved by physical fluxes, by the subduction of DIC. And I want to look at how this subduction of DIC is occurring. So how and where is this subduction occurring? What is the contribution of mesoscale and submesoscale features to these subductions? What will be the effect of a change of circulation in this subduction? And what will be an effect in the change of the physiology of the ecosystem in this subduction? So these are still open questions. I'm not going to answer to all of these questions today, but that really gives the frame of what we're looking at. So if we think of, it's a bit, I forgot to, don't read it. Just listen to me, it would be easier. if we think of the uptake of anthropogenic carbon, we can think of it into 3 steps. So the first step is you have a change in the concentration of CO2 in the atmosphere, and this CO2 is getting into the ocean. You don't need to have a change into the ocean circulation or a change in the ocean biology to have this uptake. So you just have to have a change in the CO2 in the atmosphere to have this uptake. A second step is if you have a change in the ocean physiology of the biological pump, you can have a biological pump which gets more or less efficient. So you can have circulation of the ocean which remains the same, and you can have some change in the physiology, and so you can change your uptake by the ocean. And the third step is you can have a change in the CO2 in the atmosphere, a change in the efficiency of the biological pump, and a change in the circulation. And so these different steps has to be taken one by one if we want to understand how the ocean, how the CO2 gets from the surface, from the atmosphere to the ocean. So I want to go back to this IPCC schemes that have been drawn. So this is the one from 2007 and 2013 to show you the flux I'm interested in. So this is for the pre-industrial ocean. And so these are the fluxes of DIC between the surface ocean and the deep ocean that have been estimated into these reports, and they are of the order of plus 100 and minus 90 in these 2 reports. If we look at 2 other reports in 2001 and 2011, and we look at the same fluxes, and we see that there's a factor 2 between the 2, plus 30 and 40. And so these numbers were effectively computed by Nikki Gruber and Corinne Le Quéré. So we specifically called them and asked them, well, how did you compute this? And all of them have their own recipe to compute these fluxes from, global scale numbers. And there were, in addition to this, a few regional studies that have looked at very specific regions. I can think of one by Suzanne Lausier in the North Atlantic, where they specifically looked at how physical transport were transporting the IC from the surface to the deep ocean. But clearly, before Laurent Bob and myself started this work, there was very, very little knowledge about these fluxes of the IC between the surface and the deep ocean. Just one detail which is important is what is the meaningful boundary when we think of fluxes between the surface and the deep ocean? My belief is that there is no meaningful boundary, and that what we should really aim at is to have a full description of the vertical change of the flux. The flux is changing with depth, and that's what we need. So far, when we think of the biological pump, the boundary that has a biological meaning and sense, and that has been used is the aphotic depth, because you have a very different behavior when you have light and when you don't have light. If you think in terms of physical fluxes, the aphotic depth is probably not the right boundary. The right boundary is obviously the surface boundary layer, which is the surface mix layer where all the properties are mixed. And this is important because if you think of the air sea flux, they're going to affect really the content within the mix layer and not below. So all the diagnostics I'm going to show you are across the mix layer depth, the surface boundary layer, and as you know, the surface boundary layer is very variable in the ocean, is very variable from one day to the next, and is very variable from one region to the other. So I'm going to show you fluxes across a boundary which is very, very variable in space and time. So let's go now into the details of the flux between the surface boundary layer and the deep ocean. So as I said, the surface boundary layer base here, so that's the surface of the ocean, that's the base of the surface boundary layer, and I've drawn a line like this just to show you that there are regions of the ocean where it's deeper than others, so there are strong gradients in the ocean in this boundary layer depth. So how can you exchange material between this depth and below? There are a number of physical processes, all of them. So you can either untrain or detrain. You change the depth of your mix layer. You can have vertical diffusion at the base of your mix layer. You can have vertical advection across the mix layer. You can have horizontal advection across the horizontal gradients of this mix layer. And you can have eddy mixing, the role of eddies. And I'm going to look at these processes. I will focus first on large-scale processes, meaning I will look at large-scale advection and large-scale entrainment. Everything is going to be large-scale, but you have to keep in mind that the small scales are also important. And in the second part of my talk, I will address the role of small-scale vertical advection and horizontal advection due to mesoscality and submesoscale filaments. But I'll start with the large scale. So how do we compute this? We compute this by computing all of these fluxes separately at each time everywhere in the ocean, and then we can integrate over 1 year, and we get a net subduction flux of any quantity C, which can be DIC or organic material or whatever. And what you can see from this equation is that it's extremely difficult to estimate this from observations, because you need to have consistent observations of vertical diffusivity, horizontal velocities, vertical velocities, mixed layer depths, and tracer concentrations, which you absolutely don't have. But models offer a framework where, of course, all fields are consistent and the fluxes can be estimated. And so that's one of the reasons why I'm going to focus on showing you model estimates. But I just want to mention this very nice work by Jean-Baptiste Salé in 2012 in the Southern Ocean, where they've used the best observations that they could to try to estimate these fluxes across the winter mixed layer depths. So it's possible, but it's still full of uncertainties. So I'll show you 3 different works. One focuses on the carbon transfers in the global ocean during the pre-industrial period, so when the biological pump and the physical fluxes are in balance. Then I'll focus on the anthropogenic carbon perturbation in the global ocean. And I'll finish with some things that we did in 2011 with a PhD student, looking at the role of submesoscales in the Northeast Atlantic. So to do that, I'm going to use one simulation of which is going to be a climatological simulation, so no decadal variability, very simple. The most simple simulation that you could imagine with an GCM with 2-degree resolution with a biogeochemical model for the pre-industrial ocean. And I'm going to try to compare some of our estimates with estimates from climatological data. I'm going to use DIC from GLODAP, wind, velocities from altimetry, and climatology of mixed layer depths. So I'm going to show you, so each of these 4 plots are one of these processes. So let's start with vertical mixing at the base of the mixed layer. So they all have the same scale. Blue is subduction, so meaning that the DIC is leaving the surface layer, and when it's red is abduction, DIC is being brought to the surface. So basically vertical mixing is a weak term that slightly brings some DIC to the surface everywhere in the ocean. If you look at vertical advection, it's also something which is easy to understand. You have subduction in the center of the gyres, where you have a general downwelling, and you have upwelling and abduction in areas where you have a large-scale upwelling. So that's really what you see in the map of vertical advection. The map of horizontal advection is more complex. There are more ups and downs, and you can see clearly some subduction here in the regions of mud water formation in the Gulf Stream, which is very clear, and it's more patchy in the Southern Ocean, where you know that the mixed layer shows very, very patchy, a lot of patchiness here in the Southern Ocean, and the mixed layer which creates this patchiness in the horizontal advection. So the role of eddies was estimated here in this coarse-resolution model using a closure. So that's really probably the weakest part of this estimate. This is the same estimate for horizontal advection and vertical advection from observations. And you see, at least for vertical advection, that the patterns are very similar, and also the magnitude. For horizontal advection it's more tricky to see things, because probably because of the inconsistency between the currents derived from from altimetry and the observations of dissolved inorganic carbon, so it's more difficult to do. Now let's move to the abduction and subduction of organic materials. So that's the part of the biological pump which is achieved by physical processes. What you see here is the large role of vertical mixing, organic carbon out of the surface layer below. So there's a large part of the biological pump is achieved by the subduction of organic materials through vertical mixing, and again the role of horizontal advection, eddy mixing, and etc. Now I am comparing in these 4 plots these 4 fluxes, which is first here the net subduction, abduction of DIC, which is this diagram here. The physical transfer of, this net here is the physical transfer of DIC, is this one. Then you have the physical transfer of organic carbon, which is the subduction here, the RC flux, and the biological transfer, which is the sedimentation. So just to show you that I use different scales. So these 3 have the same color bar, and the physical transfer of DIC has a different color bar. And as you see, the order of magnitude, you can see very clearly that the order of magnitude of this up and downs of DIC to the surface are much, much larger than the RC flux, than the biological pump, and that the transfer of organic carbon through the physical processes. So that's very important. Something else that you could note between this map is that the sedimentation and the subduction of organic material have the same order of magnitude. This is also another important message. There is, of course, a large regional variations, particularly in the physical transfer of DIC. To simplify the image, we've averaged over latitudinal bands, and I'm showing again this plot that Scott Donny has kindly shown yesterday in his presentation to highlight that the physical transfer of DIC in all regions is directed in the same direction as the RC CO2 flux. So you have, but it's much, much larger in amplitude. So here the CO2 is penetrating to the surface, and then there's a strong downwelling of DIC, and this is true everywhere. Another thing that you can see here, if you compare the green and red curves, is that the physical transfer of organic carbon is about 2/3 of the total biological pump almost everywhere, at least at mid and high latitudes. So now we've averaged everything over the global ocean, and we're comparing here our predictions to the predictions of the IPCC reports, and I want you to look at these 2 numbers. So it was between 40 and 100 in the previous reports. We get numbers more closer to 300, so which is much, much larger. And I'm strongly convinced that our numbers are very, very strong underestimate of the real fluxes, because in these estimates, what we have not looked at is the role of mesoscale and submesoscale. And I'm suspecting that we must have very, very strong compensating upwelling and downwelling of DIC due to this submesoscale that will strongly, strongly enhance these 2 estimates. I'm hoping that in the near future, when we'll be able to run global models at higher resolution, we'll be able to look further into these fluxes. Now let's go to the anthropogenic carbon part of the problem. And now I'm using simulations, which are historical simulation from period 1890 down to 2007. And I have 2 simulations, so they have the exact same physics, the exact same biology. The only difference between the simulation is the amount of CO2 in the atmosphere. So one has a constant concentration of CO2, the other one has a trend. And so we look at how the difference between this simulation is going to give us the flux of anthropogenic carbon. And really, I want to insist on the fact that the biological pump and the circulation are strictly identical in the 2. So if you look at the black curve here, this is the air-sea flux during the period of the simulation integrated in the global ocean. And you see, as you expect, you start from 0 and you see an increase of the uptake of anthropogenic carbon by the ocean. What's new here is the red curve, which is the total carbon subduction. So how much of this is leaving the surface of the ocean and is going below. And you can see that the total subduction is very close to the air-sea carbon flux, which means that most of the carbon does not remain at the surface, but is exported below. Another thing that you see is that there is much more variability in the subduction than there is in the air-sea carbon flux. We will see what is the process which drives this higher variability in the subduction. And this is the net air-sea flux and the net subducted flux integrated over this period. So you can cut this total subduction into the sum of these the physical processes that lead to the subduction, and this is what this is showing. So the total is repeated here in red, and the physical processes are vertical mixing in blue, advection in green, and again an estimate of the eddy contribution in light blue. What you see is the predominant role of vertical mixing. And vertical mixing, as I said, includes two terms, vertical diffusion and changes in mixed layer depth. And the large variability, internal variability, is due to the large internal variability in the mixed layer depth, in the entrainment and detrainment. There is also a large contribution from advection. It's close to the contribution for vertical mixing, but again, what's important is the large role of vertical mixing. You can now look at this from a regional point of view, and so if you just look at these two diagrams here on the top, you have the air-sea flux of anthropogenic carbon predicted by the model, and the total subduction of anthropogenic carbon predicted by the model. I think what's interesting here is to see that the air-sea flux and the penetration do not occur at the same location, and that's of course because the processes are different. So you have the physical processes into the ocean here, and this is due to winds and temperature, and so it's different, and this has really has, I think, to be accounted for. We have to go into regional analysis of how the carbon penetrates into the ocean by looking at these kind of diagnostics. So now I'm going to switch to something slightly different, which is I'm going to add some variability to my system, and I'm going to allow the efficiency of my biological pump to change. I don't want to change the physical supplies, so I'm not changing the circulation. I'm just changing the efficiency, and I'm doing this in a very controlled way by changing the carbon to nitrogen ratio of primary production in my model. And so that's the way we did it, and we have different levels of efficiency, so the biological pump can be more or less efficient. And we looked at how this changed the carbon flux to the ocean. And so the black line here is the uptake of CO2 in the ocean if you don't change the concentration of PCO2 in the atmosphere, so more or less constant. If you change the concentration of CO2 in the atmosphere, that's what we've seen previously, you see an increase in this uptake of CO2 by the ocean. And now the different colors show you how this change, this uptake, is modulated by when you change the efficiency of the biological pump by between -20% and +20%. So again, without changing the circulation, a change in the efficiency of the biological pump is affecting the uptake of CO2, and the next step, which we have not done yet, is to see how this is going to be transferred to the deep ocean. But obviously, if we change the biology of the biological pump, our model is probably too simplistic because we also need to change the efficiency of the export somehow. So going to the eddy flux. The eddy flux is really one of the big unknowns so far in this part of the physical fluxes. This is, the bottom of my slides are not, I always feel that I don't know why, but this is a paper by Anand Gynodesikan, which have looked in a model at the sensitivity of the anthropogenic carbon uptake in the model when he was changing natural eddy mixing. And his study has clearly shown how sensitive this uptake was to something which we really don't completely control. So there is some large uncertainty in this uptake. If we think of the biological physical fluxes of subduction of POC and DOC, this is a study that has been shown again yesterday by Melissa Oman, which shows very clearly from observations the subduction of particulate organic carbon and dissolved organic carbon due to submesoscales, and which suggests that this part of the subduction is also very important. They propose that maybe about 30 to maybe 50% of the biological pump could be achieved by these fluxes. So I'm going back to this program that we conducted in France in 2001. And I want to go back on this because yesterday we discussed export, and there's this idea in France to maybe conduct something similar to export at the same time, maybe in a different region, because the time frame of our programs do not allow to go to sea, unfortunately, at the same time. So one of the sites that we might go to is this POM area in the Northeast Atlantic that we've already visited in 2001. And it's an area where there's a very strong gradient in the winter mixed layer depth, and which is an area where there's a strong CO2 sink of carbon. Well, and I'm going to show you some results of this study, which looked with a high-resolution model on the role of subduction in this region. Just tell me if I'm okay with time. 4 minutes? Okay. And I'm going to compare two simulations, one with eddies here, and submesoscales and like small scale features, and one which is much smoother. And I'm going to compare the subduction in these two simulations in order to give some estimate of the role of this subduction. So this is the subduction rate computed when you have a full variability, and this is the subduction rate that you get when it's smoother. So why do we have subduction due to submesoscales? So this is a vertical section in this model showing the mixed layer depth in white, and the colors show you the vertical velocities. And you clearly see this cell of very thin vertical velocities crossing the mixed layer up and down. So you have an upwelling across the mixed layer, bringing everything within the mixed layer, and you have a downwelling cell that crosses the mixed layer the other way around. So these fluxes might be very important in the total budget and might not compensate each other exactly. So that's the flux estimates from the model when we have submesoscale. So again, this is the sedimentation of organic material, which is 2 in units of micromole of carbon per square meter per year. If you compare it to subduction, the total subduction is 66. It's very small compared to the subduction of DIC. So again, most of the carbon that leaves the surface layer is mostly under the form of DIC and mostly through subduction. And the difference between these two, 64 and 66, is the amount of subduction of organic material. So you have sedimentation of 2, organic material through subduction of 2, and subduction of DIC of 64. Now that's when we have submesoscales. If we remove the submesoscales, that's how the numbers have changed. The numbers don't change in terms, the biology is not changed very much in this region, surprisingly, when you remove the submesoscales. So sedimentation remains more or less the same, and the subduction is slightly reduced by the order of 10%. So we have a small reduction in the subduction when we remove the submesoscale. This, of course, is only a very regional study. The only thing we can conclude from this is that we need more observations of this submesoscale subduction. It might be important, it may vary from one region to the other, and it's really one of the large unknowns that are still, that we still have to investigate. So just some conclusions. I would say this model study suggests that we need to be aware that physical fluxes are important. it's not only the biology that enables carbon to leave the surface and to go to the interior. At temperate latitudes, more than 90% of the carbon flux to the deep ocean is due to the subduction of the ice sea. The rest is by sedimentation. So the physics is crucial. These are estimates from a model, of course, and we can refine them, and hopefully we will refine them when we'll have observation. But it's just to highlight the importance of this process. It could be that 1/3 of the organic carbon export is through subduction. It could be that there is more because we have not accounted for submesoscales. And then another important message is that the anthropogenic carbon flux between the ocean and the atmosphere and between the surface of the ocean and the deep ocean are close in magnitude, but they do not occur at the same location. So we have to also follow the path of this anthropogenic carbon penetration in the ocean. Some open questions, there are lots of open questions, but I think I've mentioned this before. We know very little about the contribution of submesoscale to the export of the ice sea, of dissolved organic carbon, of particulate organic carbon, and of anthropogenic carbon. We know very little about the vertical structure of this physical export. We have to investigate this. And also what we don't know is the interplay between the changes in the physical fluxes and the changes in the efficiency of the biological pump, the changes in the circulation, and all of these has to be accounted for together if we want to have a full understanding of the carbon fluxes in the ocean and how they're going to evolve with time. Thank you very much.
So I've been told that we are allowed one question before the coffee break.
Yes, I was wondering if you could comment a little bit on the role of eddies, of mesoscale eddies, on the DIC fluxes. At some point, you said that they were going in the opposite direction. I think you're discussing CO2 fluxes, was it, or were you discussing the DIC?
So the role of eddies, you mean in the models that I've shown before?
Yes, where the eddies were.
Or you mean, just the diagram?
So you had an eddy, was it ARC CO2 fluxes or DIC uptake in the ocean, and the eddies were going in the opposite direction?
I think my main point is that you have to see that the circulation, what's doing the subduction is the circulation. So you can cut the circulation into large-scale currents and mixed layer, and so you can compute your subduction by the large-scale currents. But then you have very small currents, horizontal. You have plumes, you have these plumes of vertical velocities which are crossing the mixed layer in both directions, and these are not accounted for in the large-scale circulation. And their role in the subduction of the IC, I will say, is really still completely unknown. We know from some studies that the downwelling velocities associated with this submesoscale are clearly exporting organic material from the surface to the deep ocean. For DIC, we know much less. There was this study that I've shown in the Northeast Atlantic that suggests that if you average things, they might increase the total subduction of DIC to the ocean, but that's very specific to that region. And on the global ocean, I will not be able to give you an order of magnitude either.
Yeah, I guess I was thinking more of the mesoscale as opposed to the submesoscale. So I see how in the Southern Ocean the eddies, right, oppose the mean circulation and so forth. So they will have opposite effects from the mean flow on the fluxes and uptake. But is that the case everywhere?
That's really
else?
From a parametrization. So you have to take this very cautiously, I would say.
Okay, thank you.